So for this last example, I want to look at a distributed load. It has a pin at A, a roller at B, and then there's this overhang at C, and then we have this applied moment at the end at C. So this one's a little more complicated, but we're going to use that same method of cuts to find the shear and moment diagram and the equations for shear and moment as a function of x as we move across this whole beam. You'll see on here that I have already solved for the reaction force at A and at B. I'm not going to do that. You should know that how to do that from before. The first step is to take a cut between A and B. So I'm going to take some arbitrary cut between those two. So we'll call this cut 1. And now I will draw the free body diagram for cut 1. Okay, so here's the free body diagram. One thing I wanted to point out is I actually had these values reversed in our free body diagram over here. This should be 10 kilonewtons and this should be 30 kilonewtons. So I've corrected it and put it on this free body diagram. So you'll see with this free body diagram I have my distributed load, I have my pin force of AY, I have some value of x. Again, it's between 0 and 16 meters. And I have my internal forces of V1 and my moment M1. So the next step is to find our shear for this range, and we will sum forces in the y direction, set that equal to 0. We have 10 kilonewtons plus, and then we have a minus 2 times x. That is our force right here. That is the distributed load, which is just the area under the curve. And then last we have our minus V1. So if I rearrange this, I have V1 equals 10 kilonewtons minus 2x. That is the equation for the shear along x between that range. Okay, solving for our shear at x equal to 0, we find our shear to equal 10 kilonewtons, plugging back into this equation, of course, and at x equal to 16 meters, we find our shear to equal a minus 22 kilonewtons. Okay, so that's important for us also. Next, we want to solve for the moment. To solve for the moment, we have the sum of the moments at our cut 1 equals 0. We have M1. We have our, which is positive, we have a negative 10 kilonewtons due to the reaction force, the pin, times x. And then we have our load F2, which is plus 2x is the load, and the moment arm is this distance here, and that distance we need to determine. And if you think about it, that distance for this centroid, right, this load is at the centroid, is x over 2. It's always half that overall distance. So this becomes our x over 2. Okay, and now we can solve for M1, and we get 10x minus x squared. So some parabolic function. Okay, between 0 and 16 feet. So now if we analyze this at x equal to 0, our moment at M1 equals 0. At x equal to 16, not feet, meters, sorry, M1 at that location equals a minus 96 kilonewton meters. So those are important values to look at. Okay, so now we've gone through and evaluated up to this point at B. The next location that we want to look at would be where we see a change, and that change again happens at this 30 kilonewtons. So we're going to make a second cut here. This is our cut 2. And that, of course, is for cut 2, is between our 16 and 20 meters. I'm going to draw that free body diagram for that section. Okay, so here we have our free body diagram for this next cut between 16 meters and 20 meters. You'll see we've added in this reaction force of 30 kilonewtons. We have our shear still out here and our moment. And now we want to solve for the shear. So we will sum forces in the y direction. If we do that, we have some of the forces in the y direction equals our 10 kilonewtons plus 30 kilonewtons minus V2. And then this distributed load again is this force. And that force is the area under this curve, which is 2 kilonewtons per meter times x. So that is a minus 2x. Now we will solve for V2. So here is V2 as a function of x from that cut. And now let's evaluate this at x equal to 16 meters and x equal to 20 meters. At x equals 16 meters, V2 equals 8 kilonewtons, and at 20 meters, this equals 0 kilonewtons. Okay, so now we have to look at this and solve for the last part, which is looking for our moment M2. The moment M cut 2 is equal to 0 is equal to our minus 10 kilonewtons. It's going to cause a negative moment. At x is the moment arm. Then we have the 30 kilonewton force. That's kilonewtons times this moment arm, which is x minus 16. And then the last part we have is this force again, this force F2 of the distributed force. That's going to cause a positive moment. 2x is the force. And the moment arm is, again, this distance here, right? It's this distance from here to here, which this is at the centroid. So, again, that's still just x over 2. And then last, we have, of course, our moment M2. And now we can solve for M2. Here's what we get when we solve for M2. Now we want to, so that's our equation in terms of the function of x. Again, it's some quadratic at x equal to 16 meters. If we solve for that, M2 is equal to a minus 96 kilonewton meters. At x equal to 20 meters, we have our M2 is equal to 80 kilonewton meters. So now we can plot all of this information also. Here's our shear one for this range, and here is our moment information. So let's go and plot that. So we'll start with the shear and go through the shear. We see at 0, it is 10 kilonewtons, so it starts out at 10 right away, and then it goes to, at 16, it goes to a negative 22. So if we come down here, that's a linear equation that comes like this. This is 10, that's a 10, and this is a minus 22 kilonewtons. And then we see, if we look at the second part, it jumps up to 8. It's discontinuous, jumps up at 8, and ends at 0. So it will jump up to some amount 8, and then end back at our end here of 0. So this is 8. Okay, let's look at this and plot our moments. We see that it starts out at 0 and ends at a minus 96. So it's starting here and ends at some low value down here of minus 96. And that occurs here. Now, how do we get there? If we actually plot it, we could put it in to a calculator and plot all these points. We see that it will come up something like this. And we'll learn in the next section on how to be able to plot this a little better too. And then at the end, the very end, we see that it starts out with our moment at the same minus 96 and ends at a negative 80. That should have been a negative value there, sorry. Should have ended at negative 80. And we'll come out like that. So this is negative 80, negative 96, starts out at 0. So one thing we don't know is, what is this value at this peak here? How do we find that? We see that it is located at the same location where this crosses the 0 axis. So if we know that location, which we can find that maximum. So how do we find that? Let's look at our equation here for our shear. And we see that this V1 equals 10 kilonewtons minus 2x. And if we set that equal to 0, when our shear is equal to 0, we can solve for this, right? We have 2x equals 10, or x equals 5 meters. So that's where that is located, is at 5 meters. So that is also here 5 meters. If we put this back into this equation for the first cut here, sorry about that, back into here, this m1 equals 10x minus x squared. If we put in 5 into there, we can find m1. And if we do that, m1 will equal 25 kilonewton meters. So the other point that we want to put on here is this value here of 25. So that gives us the full diagram for this beam.